Okay, welcome to Lecture 5 of the Controls Classroom. This week I don't have much in the way of notes. The only thing I want to say is that this will probably be the longest lecture yet. There is a good stopping point that will hopefully be midway through, and so I'll let you know when that is if you want to just do one part today and then do another part the next day. So the first half of this lecture and the first thing that I want to talk about is Git. So Git is a program that serves two main purposes. The first one is distributing code between people, and the second purpose is versioning code. And we'll sort of get into what versioning means as we go through this lecture and do the demos. Git is almost ubiquitous in industry. If you go into a career in programming or software engineering, I would think it is exceedingly likely that you're going to use Git at some point. And so Git kind of deals with these big concepts, but they're really just built up from simple ideas. So we're going to try to build up these simple ideas in the same way to end up with the concepts that Git deals with. First thing to address is, why do we need Git? It makes it really easy to distribute code, and we need to distribute code. When we have 4 or 5 people working on the robot, it's not like we can all be typing on the same laptop at the same time. We kind of constantly need to sync our changes back and forth from our personal laptops, and so we can work in parallel and be a lot more efficient that way. The other thing that we need Git for is distributing code like between our laptops frequently, or doing that frequently will lessen the impact of data loss. So if somebody's laptop gets stolen or if a hard drive fails, it's not as big of a deal because we have numerous copies of the code in different places and we can easily restore from one of those copies. We also need to version code, and so this will get into what versioning means a little bit. Let's say we're working on an experimental feature for the robot and it doesn't work. And if we've made changes all throughout the robot code to support this feature, it could be really tedious to go through all those locations and undo it. Excuse me. So if we can create versions or like snapshots in time of the code base, it's really easy to just go back to the old version, but we can still save the progress we made on the experiment in a new version in case we want to revisit it later. So if you think of having a stable version here where we make an experimental change, we can always go back to the stable version while still saving the unfinished experimental code in an experimental version. So let's sort of dig into how Git works, and how versioning works in particular. So Git takes a snapshot, which is like a copy of all your source code. And each snapshot remembers the snapshot that came before it, just prior. So it knows where it sort of came from in terms of like the order of the versions. Snapshots are immutable, which means that once you create them, they never change. You can create more, but you can't change them after you create them. And snapshots in Git are known as commits. So you can imagine you have your initial snapshot, your initial commit here, and you add another one. And you might wonder why this arrow is going backwards from right to left. This is signifying that the second commit remembers that it came from the initial commit, that that was the most recent commit before it was created. And you can see that if we add another one, it remembers it came from the second one, and so on and so forth until we get to the latest one. And so the latest commit is also known as head. And so time is going like left to right. The initial commit is obviously older than the more recent commits, but they're all remembering where they came from, and you can kind of get this backwards record. So let's actually use Git to make some commits. So if I pop into Ubuntu here, you may or may not have Git installed. If you don't have Git installed, you just want to run sudo apt update and then double ampersand and sudo apt install -y git. I already have Git installed, so I'm going to skip this step, but if you're missing it, this is what you want to do to install it. The first thing we need to use Git is a directory to actually store the source code. So I'm going to make a directory called robot code, and I'm going to go into it. And once I'm here, I'm going to run a command called git init. And so this directory, robot code, will be known as the repository for our code. That's kind of what Git likes to refer to it as. And so when you do git init here, you can see that it is initializing a repository. So let's start putting some robot code in. I think we're going to need a file called robot.cpp, and we don't have to put anything in it right now. Let's just make an empty file. I can run git status to see sort of what Git thinks the status of the repository is. And so it says that it has this untracked file called robot.cpp, but we can use git add to track it. So that's what I'll do. I'll follow the instructions it gives me and run git add robot.cpp. And if we do git status again, you can see that it has changes to be committed. So these are the changes that it will track if we commit them. And it's saying that it detects a new file, robot.cpp. And so that looks right to me. So I'm going to do git commit -m for message, and I'm going to say added empty robot code as sort of the message. And so Git's going to complain. It's going to want to know our email and our name. And this is not signing us up for anything or anything like that. This is just getting this information so that it can record us as being the author of the commit when other people go and look at it. And so I've already run these commands. I'll just run them again. So I've sent my email, I'll also sent my name. And we should be good to go to run the commit again. And so this is what it looks like when you commit something. If we run git status again, it says that we're on a branch called master. That must mean something, and that there's nothing to commit. And that makes sense, because nothing has changed since we last made a commit just now. If we go to git log, we can see a few things. We can see that we have this commit, and that, well, it's marked as the head, and it's also got this master thing attached to it. And we'll get into what that means in a second. It's got me as the author, which is accurate, and it's got the time, which is accurate, and it's got the message we gave it. So let's make more commits. What if we wanted to fill out the robot file a little bit more? And so I'll just add a main function to it. And it's just going to return 0. It's not going to do anything. It's just going to quit immediately. But that's fine. If I do git status again, Git is actually picking up on the fact that we changed it. And if we run this command called git diff, that'll tell us exactly what Git is seeing that changed. You'll see these lines have pluses next to them, and that means that Git is seeing that there are new lines in the file that are not there in the previous commit. And so this looks like what we'd expect. So I'll add robot.cpp again, and I'll commit it with some kind of descriptive message. Something like that. And now if we do git log once again, you can see that it's got our empty robot code commit from earlier, but it also has the new function we just created, or the new commit that we just created, and it's also marking it as head once again. So the latest commit is always head. We could have a situation where multiple branches share the same parent, and this is allowed, but it's hard to remember which commit is which. Maybe we are like using commit 2 and we're adding commits on top of commit 2, and then we want to switch to commit 3 and start adding commits on top of commit 3 instead. I mean, when we're just using numbers like 1, 2, and 3, it's pretty easy, but if you look at the way Git actually creates commit IDs, these are pretty complicated and hard to remember. So if you have hundreds of these, it would be especially difficult. So what Git does, it provides a mechanism called branches to keep things organized. And so a branch is like a variable that holds a commit ID. That's one good way to think about it. And so the current branch always stays in sync with the head commit. And so if we look what we were doing in Git earlier and we run git status, it's telling us that we're on a branch called master. And you'll notice that as we committed, not only did the head stay up to date with the latest commit, but master also stayed up to date with the latest commit that we made on master. So hopefully that makes sense. So let's give an example of branching using more than one branch. So let's say we've made an initial commit on master, and we make another, and as expected, master has moved to the latest commit. Let's say we create a new branch called myExperiment, and we change our current branch to myExperiment. So now both master and myExperiment are pointing at commit 2. If we make a new commit on top of commit 2, myExperiment will move to point to commit 3 because it's the current branch, but master will still commit at commit 2, will still point at commit 2 because it's not the current branch. And so I can actually illustrate that exact behavior in Git. If I run the command git checkout and then -b and then myExperiment, I can break down what this means. Checkout means to switch to a new branch, or switch to a branch that may or may not be new. This B is actually the part that tells it to make the new branch. So I'll do that. And it says switch to a new branch, myExperiment. And so if I do git log right here, you can see that both myExperiment and master are pointing at this commit. So in the slides, that's kind of like what we saw here, where both master and myExperiment are pointing at commit 2. We've got the same thing going on in Ubuntu here. But now let's say I want to actually make a new commit on the myExperiment branch, where I'll have the robot actually print something out in its code. I'll have it say hello from the myExperiment branch. And let me actually have the operators here. Cool. So if I do git status again, you'll notice that it did pick up on the file changing, and if I do git diff again, it does pick up on the new lines that I've added. So those look good to me. So I'll add it and I'll commit it. Give it a nice message. And now if I look at the log, you can see that the latest commit here is what myExperiment is pointing to. The old commit is what master is pointing to. And so that kind of reflects this state in the slides, right? The next thing I wanted to talk about is merging. So Git can merge the contents of one branch into another. And so how does it do this? Well, it finds the common ancestor between the two branches. So if you imagine way back here, where commit 2 and commit 3 are splitting off from commit 1, commit 1 would be their common ancestor. And so what it's going to do is it's going to look at all of the commits on the source branch from the common ancestor to the head. So everything that has been committed on the source branch after the point where the two branches diverged, if that makes sense. And it's going to roll them up into a single merge commit. And then it's going to plop the rolled up commit onto the target branch. This works well, but if you have files being changed on both of the branches, we're going to get a merge conflict because we don't know which one is the right one or which one we want to modify, and that has to be manually resolved. So let's do an example of a merge. We have a common ancestor here, and we have master here, and my experiment here, and they've both got a few commits on them. They've kind of diverged a bit. When we want to merge my experiment into master, we're going to take all the commits on my experiment after the split point, and we're going to roll them up into a merge commit. And then we're going to take that merge commit, and we're going to plop it right on top of master, and this becomes the new head and the new thing that master points at. Now, where this doesn't work is if you have a conflict. And so I'm going to try to illustrate what that conflict could look like. So if we go back into Windows here, I'm going to go back to the master branch. I was on the my experiment branch. I'm going to go back to master just by running git checkout master. And you can see it's switched. And if we run git log, we have no knowledge of this welcoming message thing because it's not in the record from what master is pointing at. Like master points at this commit, and this commit points at the previous commit. That welcoming message is not going to be part of that history, if that makes sense. So let's say we're totally unaware of the experiment, and we are working on our robot code, and we also decide to add a message. But we decide to add a different message. Say something like that. And we look at the status, and we look at the diff, and we go through all the same motions of committing it. And we put in some commit message, and we look at the log. Can see that everything is looking good so far, as you'd expect. Now let's say we decide to merge the experiment branch into the master branch. And so the way you merge in Git is you get on the branch that you want to merge into. So we're already on the master branch, which is good. And then we say git merge, and then we say the branch that we want to actually merge in. So we want to merge in my experiment. And so if we run this, we got a merge conflict in robot.cpp. And so what this actually looks like when it happens is you're going to see some changes in robot.cpp. And it's going to look like this. You're going to have all of these left arrows and right arrows and equal signs. And what it's saying here is that on head, we had 1538 rocks, but on my experiment, we had hello from the my experiment branch. And so we have to decide how we're going to resolve this conflict. And so really, we can do anything we want in this file to change it, and it's going to end up being however we leave it. So I'm going to resolve this by saying hello from the master branch, team 1538 rocks. And so this is like an example of how you could resolve something by kind of combining elements from both branches. And so I'm going to save this, and if I look at the status again, it's saying, oh, we have unmerged paths, use git add to mark resolution. Well, I just resolved the conflict, so I'm going to use git add on that. And then I also need a commit message, so I'm going to say merge in my experiment branch for the merge commit. And so now, if you look at the log, you can see that it's got this merge commit here, and it's now got everything from the My Experiment branch also added to the history. Merge commits are kind of special because they can have multiple parents. So going back to the slides, there's also something called rebasing. And rebasing is another way of combining branches like we just did. It still requires manual merging. If changes are made to the same files on both branches, you still have to manually go in and do that resolution process I just did. But the way it works is that instead of creating a merge commit, it changes the base or the parent of the commits on the source branch to the head of the target branch. So it's like if we go back to here, it would be like taking all these commits that are only on the My Experiment branch and just trying to copy and paste them on top of our progress on master. And so you might wonder, how is that possible? If these are just snapshots of all of our code, aren't we just going to blow out everything that we had on master so far by like copying and pasting these on top of it? And the answer to that is, well, I kind of told a lie earlier. And commits are not complete copies of the repo. They're not actually a snapshot of everything. They're only a snapshot of the things that changed since the previous commit. So we can actually rebase and copy and paste those commits on top of the target branch because we're only applying the changes, not actually overwriting things that didn't change. Rebasing does not create a merge commit because you're doing this copy and paste thing, but if you get a conflict, it forces you to modify sort of the pasted commits that you're using. This is not super important to really deeply understand, but it's good to know about right now. As long as you generally know how merging works, that's going to have you good to go. So let's talk about what we just covered with versioning. We have some big ideas in Git, mainly commits, branches, and the idea of merging or rebasing. And we've seen a few Git commands, init, status, add, commit, log, checkout, merge. And we didn't see rebase, but the semantics are pretty similar to merge to use it. Next thing to talk about is distributing code. So Git can synchronize the commits or the commit history on a branch with another computer. And the computer that you're synchronizing with is called the remote. So you can push to the remote to make it match your history, or you can pull from the remote to make your history match its. So a question that could come up is, what if two people push to the same remote branch at the same time? And one of them is going to get there first, and they're going to be the winner. And the other one will not, and they're going to get an error message. And the one who fails and gets the error message will have to pull in the winner's commits before they can push again. And so from here, when they do the pull, two things can happen depending on how Git is configured. We can either create a merge commit to introduce the winner's commits, or we can rebase on top of the winner's commits. It's kind of just like combining branches. But either way, if both the winner and the loser in this scenario have modified the same files, the loser is going to have to make manual changes to fix any conflicts. Now, for this merge versus rebase on pull, we actually prefer to do the rebase because we don't want unnecessary merge commits like kind of cluttering up the history. Rebasing won't create those, and we can actually configure Git to rebase when we pull. So let's actually configure that now. So we'll just run git config global pull.rebase true. I'll just run this command, and that's all there is to it. We don't have to worry too much about it. The next thing I wanted to talk about is GitHub. So GitHub is a free service that acts as a Git remote for you. It's basically free storage space for your code, and you can use it as a Git remote. So let's get that set up right now. So here I am logged into my GitHub account. And one thing that we need to do is set up a sort of key that gives Git access to our GitHub. So if you haven't made an account yet, do that. And the next thing we're going to do is go to Settings. And then we are going to go to this section here, SSH and GPG keys. And we're going to click on a new SSH key. And we'll leave this here for now. We have to go back to Ubuntu, and we're going to run something called SSH keygen, -b, and then we'll do, let's do 2048 here. Don't worry too much about this. And it's going to ask where we want to save the key, and it's got a default here. We're just going to leave it there. And we also want to put a passphrase on it. So I'm going to put a passphrase on mine. And so it's saying that your identification has been saved to some path and your public key has been saved here. And so we want to get the public key. You never want to share your identification with other people, but it's okay to share your public key with other people. So I'm going to get my public key here, and I'll print it out. And I'm going to copy this, and I'm going to paste it into GitHub here in the key section, pasting the whole thing, all these bits. And I'm going to give it a title like Controls Classroom VM, but ideally this should identify which computer the key is on. So name it accordingly, and I'll add it. It's going to ask for my password again, so let me grab that real quick. Sorry about that. Forgot that it does this. Give me a sec. Hope I typed that in right. And yeah, we've added the key here. So that is good to go. And I'm not going to save that. If I go back to the slides. The next thing I'm going to do is review some solutions from the previous lecture. If you have not finished the code for that yet, no worries, just pause the video here and then come back when you've done that, because we're also going to be doing some stuff with GitHub that's predicated on having those solutions done. So I'll just share what I did. So I'll pull that up in VS Code here. So the first problem was to write a program that asks for a name and then says hello name exclamation point back in response. This is pretty straightforward. It's just using cout to ask, and then cin to get some input, and then cout to say hello again. The next thing was the random number guesser. So generating the random number, I just followed the examples from CPP reference. I generate a random number here, and then I ask the user to try to guess it. I use cin to get their input, and if their input is equal to the number I generated, I say that they won. If it's not, I say better luck next time. So I feel like this is also pretty straightforward. I think most of the challenge here was just referencing the example code from CPP reference. But I mean, you guys are the ones doing the work of actually writing the business logic here. And then for the calculator, I took a really straightforward approach where I ask for the left operand, I ask for the operation, and then I ask for the right operand. And then I check each case for the operation. So if it's a plus, the result is the left plus the right. If it's a minus, it's the left minus the right. And then multiplication and division follow the same way. And then I print out the result at the end. And I guess I didn't add a unique feature, so I actually failed at my homework, but I'll try to be more faithful to it in the future. So the next steps from here are to create a private repo on GitHub and add me as a collaborator, and then you want to push your solutions to that repo. So I'm actually going to do that myself for my own solutions, and I'll give an overview. So if I go back to the GitHub homepage, actually I just want to go to the plus over here, and I want to, oh sorry, let me switch to Windows. So here I am on GitHub. I'm going to head over to the plus in the top right, and I'm going to click New Repository. And I'm going to call it Controls Classroom Solutions, and I'm just going to make it private. And I'm going to create it. And it's got some instructions for me. Let me zoom in on this. I'm really just concerned with this quick setup thing here. I'm going to copy this, and I'm going to go into Ubuntu here, and I'm going to back out of this robot code directory I made, and I am going to run git clone, and then I'm going to paste in that URL it gave me. And it's going to ask, do you want to trust this? Just say yes here. It's going to ask for the passphrase for the key you made. So I'm going to enter my passphrase. And it says, warning, you appear to have cloned an empty repository. That's totally fine. I am going to open it with Explorer for Controls Classroom Solutions. And I'll also just do this visually because it's convenient. Open C++. Windows is not being nice to me today. Well, what I'll do is I'll I'll actually just move the files from C++. So I'll do calculator.cpp, I'll move that into the Controls Classroom Solutions, and I'll also get hello name and random guess in there. And now if I go into Controls Classroom Solutions and I do git status, you can see that we've got all these as untracked files. So I'll just add them all, and I'll actually just add the current directory, which will catch all of them. If you look at status again, it says that they're ready to be committed. And I will commit them with the message lecture 4 exercise solutions. Now I actually need to push these to GitHub so that they're available on GitHub. And so what you do to do that is you just say git push, and then you say the name of the remote. Conventionally, the name of like a central remote like GitHub is origin. So I'm going to type in origin, And then I'm also going to say the branch that I want to push. And the branch that I want to push is the only one available, which is master. So I type in master as well, and I send it. It's going to want my passphrase again. I'll just pop that in. It's going to give a bunch of output, but it's going to say that it's pushed now. So if I go over to GitHub and I refresh this page, you can actually see that I have added commits, and these are now visible on the website. So we made this a private repo. What you need to do to share it with me is go to Settings, and I think Manage Access, and you want to invite a collaborator, and you can just invite Connor Worley altogether. Obviously it's not letting me invite myself, but this will let me see your solutions without like sharing them to the whole public, which will be really good for keeping the class going forwards in the future. So please do invite me. Okay, and the last thing is that if you want more practice with Git, there's this website called Learn Git Branching, which actually sets up a Git console or a terminal in your browser and kind of directs you through a bunch of Git commands and workflows. So I would recommend doing that. And I'll have this linked on the web page as well as in the slides. Okay, the next thing I wanted to talk about was C++. So we're about 36 minutes in-ish, and if you want to take a break and watch this part another day, that's perfectly fine, or if you just want to keep watching now, that's great as well. So C++ supports fixed size arrays of data, and you need to know the size at compile time. And so these are useful for sort of modeling data that's fixed size in real life. For example, you could have the weekly forecast of temperatures, or this could be actually recorded data. And so what we're doing here is saying that we have 7 things in the array, and that they're floats. And so these could be like temperatures that were recorded over a week. So this is what an array typically looks like in C++. The first element in the array is said to be the 0th element. So if we want to print the first element in the array, which would be like this 71.3 here, we say weekly temperatures and then 0 inside these square brackets here. And we can kind of use the same syntax to update the array. Maybe we want to correct some data and this was actually 80 degrees. So we update that first element, and we could do this all the way 0 through 6. There are 7 elements and we start at 0, so the lowest is 0 and the highest index we can go to is 6, right? So hopefully that makes sense for arrays. Another thing I wanted to talk about are loops. So how could we get an average temperature for a week given an array of temperatures? Do we like write code that adds the 0th element and then the first and then all the way up through the 6th and then divide by 7? Well, that would be like pretty tedious to write out. That's a bunch of lines of code. One thing we could do is use a loop. So I'm going to kind of break down what's going on here. This is called a for loop. And so it's got 3 parts inside the parentheses here. The first part is saying that we start with this integer I and its value is 0. And the second part is saying that as long as I is less than 7, we're going to continue looping. And then this part at the end is saying that after we finish a loop, we increment I by 1. We add 1 to I. And so what it's actually doing is running this code in the middle every time it loops. And so it's saying total and then plus equals, which is just like total equals total plus weekly temperatures, and it's looking at the ith element. So if you think about what this is doing, I is going to start at 0, it's going to add the 0th element to the total, and then it's going to do I++, which makes I 1. And then now it's saying, well, 1 is still less than 7, so we're going to do that again, and then I++ again, so now it's 2. 2 is still less than 7, 3 is still less than 7, all the way up through 6, and then it's going to do the 6th element, it's going to do I++ again, and I will become 7, And 7 is not less than 7, so it finishes the loop and starts executing later code. So that's sort of how a for loop works in C++. Sometimes we just want to run code until a condition is met. So if you think of this program where it's like, is the work done yet? As long as the work is not done, we continue looping. And if the work is done, then we indicate that the work is done in this Boolean, which will stop evaluating to true once we set it to true, because we're inverting it here. Or we could have a program that just runs forever. It just loops forever. This could be good if we want to repeatedly ask for user input and then give some output just until they decide to quit manually. So hopefully that's a good description of loops. I know this is going a lot faster than Git, but hopefully it's simpler to understand. The next thing I want to talk about are pointers. And so to think about what these even are, we want to ask, how do programs interact with the computer's memory, or like its RAM? And we can kind of think of memory as a giant array. And pointers are variables that let us access that memory array. And so if you look at this, this sample code here, we could have a float called holy cow that has a value, and we could have this float star thing called holy pointer, which is equal to ampersand holy cow. Well, what does that mean? What this means is that that star, this asterisk here, means that holy pointer is a pointer, and it's pointing to a float somewhere in that big memory array. And what this ampersand means is that it's basically going to evaluate to the location of holy cow in memory. So holy pointer stores a location in memory, and we know that what's at that location is a float. That's essentially what we're getting out of this pointer. And so if we put an asterisk in front of holy pointer like this, that's basically saying to go to that location in memory and get the data type that's there. And so if we do that, it's actually going to print out what was in holy cow. Hopefully that makes sense. It adds a level of abstraction, basically. So what happens if you just print out the pointer itself without actually going and getting the data? I would try this for yourself to see what it does. So now that we can, we kind of understand how memory works and pointers work, we can start talking about like how to use memory, or maybe abuse it in this case. So for example, what if we want to store data in an array, but we don't know how much data we're going to get until the user tells us? You could think of a program for reading some data for a file and then doing some array transformation. We don't know how big to make the array until we actually read it. Well, we can actually, at runtime, reserve some space in memory and use that to store an array. And we can vary how much space we reserve based on user input, or things that we don't know until runtime. So for example, we could have some code like this, where we have a number of samples, and we're going to ask the user for how many samples we need to store. Sorry for these backwards arrows, they should be going the other way. And now what we can do is we can use this keyword called new to make a float, and the size of that float array is going to be n samples. We're also using this keyword here called auto. And auto is basically letting the compiler figure out what the type of data is on its own, and it can do that because we're basically telling it on the other side that it's a float of some, it's like an array of floats. And then later, we've reserved some memory using this new thing, and we want to free that memory up later, so we need to use delete. This is a horrible idea in practice. You can write this code and it'll compile, but you don't want to do this for several reasons. The first one is that every time you have a new that reserves some memory, you always need the delete. If you forget the delete, it's just going to reserve that memory and it's going to hang on to it forever. And so if you have this in a loop or a function that gets called a lot, it's going to keep reserving and holding that memory and never letting any of it go until your program eventually crashes because it's using all of the computer's memory. This is also kind of annoying because here we're making an array of floats, and so we need to use the brackets on this delete keyword. Normally, if you're making just a singular data type that's not an array, you don't put the brackets on delete here. And you always need to make sure you're using the right syntax depending on what you're reserving. So new and delete are just generally a bad idea, and I think you should avoid them in every case. So let's talk about what the right way to do this is. C++ gives us some better options, and here's an example of that. We need to include this memory header, and here's the same idea of reserving a float array big enough for n samples. We use this thing called standard make unique, and we put this little float array indicator here, and we put n samples here. And once again, we can use auto for this because we're kind of telling it on the other side that it's going to be a float array, and so we don't need to write that more than once. And so let me explain what's kind of going on that makes this better than using new or delete. And the reason is that everything between a left squiggly bracket and a right squiggly bracket in C++ is called a scope. So if we look at the main function, we have a left squiggly bracket and a right squiggly bracket. Everything in between those is called a scope. So we have a scope here. And what make unique does is that it returns a special unique pointer it automatically releases any of the memory it reserves when the scope that it's in when execution reaches the end of the scope that it's in. So you think your code's actually running, it's moving along through the main function. As soon as the execution of your code hits the end of the main function, the unique pointer that make unique creates is smart enough to detect that it's going out of scope and will automatically free up that memory that it reserved earlier. New and delete are kind of holdovers from C before we had the wisdom to invent these new unique pointer types. And if you ever see anything online that's using like malloc or free, these are literally from C, and they're just as bad as using new or delete, so please avoid them. So I have some next steps for the C++ side of things. And the first project is to update your calculator program to run forever. So you want to use the results of previous calculations as the inputs for the next calculation. So if you run 3 and then times and then 4 and it gives you 12, if I put in +1 after that, it should give me 13. It should use the previous results as the next operands, if that makes sense. The next thing I want you to do is to create a program that will handle student test scores. So it should ask the user for the number of scores they want to input, and then it should ask them however many times to input those scores, and then it should calculate the average and print it. But not only that, it should also print all of the scores on a single line, comma separated. So once the user's kind of typed in, I want to enter like 7 scores, and then it's entered all 7 of them. Once they've entered all 7 of them, you want to calculate the average and print it out, and then also print all 7 on the same line, comma separated. And then once you've done that, please upload code for both programs to your private GitHub repo. when you do this, do it on a separate branch from master, but don't merge it into master yet. This is really important because it's going to lead into how we're going to use GitHub next week. So I hope this lecture did not run too long. I tried to be pretty comprehensive without going too deep into some details. So yeah, thank you for watching all the way through.